Hello, good evening, my 12th standard warriors. Time to talk about more electronic devices, transistors, the logic gates, and the operation of logical circuits, and also the Boolean algebra basics in today's session with me, Shreyas, your physics master teacher. Welcome to lecture number 2 of Semiconductors and Electronic Devices. And you are watching the Pathfinder series, last lecture of our Pathfinder series on your favorite JEE Enthuse channel. So JEE Enthuse is a dedicated English medium channel for all the aspirants preparing for all the competitive exams, and Pathfinder is a long-term series of 12th standard for free on YouTube. Welcome Blessy, hi Ankit, and hello Arunmati, hi Sai Ganesh, Solavendan. Ankit, you are not alone. We are a big family of 90,000 plus students and we are all here with you. So always try to make sure you attend the classes. You will feel lively. You will feel that many students are with you. We all are your friends. We are all your, helpers. We are all your, caretakers. So don't feel alone. We are always with you. And when you are studying, don't think about anything else. Just focus on studies. Eventually, you are going to have a good day. You're going to enjoy a quality life in IIT. So let's get going. Don't worry, my warriors. And in today's session, what we are going to do is we are going to see the PN junction diode and its applications like Zener Diode in reverse bias and voltage rectification. And then we are going to move on to transistors. How is it made? What is the symbol and how do you make it work? And what is the application as an amplifier? And then we'll also go to Boolean algebra, logic gates, and the zeros and ones that you have in machine languages. All of this with me, Shreyas, your physics master teacher at Vedantu. And if you want to know more about me, you can definitely read this out. You can follow me on my Instagram handle. And yep, here I am on YouTube to teach you in English and making sure that you guys get quality education no matter where you are. Yep, and if you love this channel, if you love the way I teach, and if you enjoy my lectures, you know what to do. A small favor, a Guru Dakshina, the fees for the channel is hitting the like and hitting the subscribe button. Thank you so much. Hello Nizake Bhatt, thank you so much for your hearts, bacha. And I'm so glad, Ankit, you're boosted up. And hello Modern Man, how many lectures of semiconductor? This is the last lecture. Hi Bharni, welcome aboard, welcome aboard. So I hope you have watched the previous class of semiconductor lecture 1, okay? And I'm pretty sure after these sessions are over, after the Pathfinder is over, you're all excited for more amazing sessions of problem solving, one-shots, mock tests, which are going to follow in the days to come. These are your essential building blocks to achieve great ranks like the students who over here, you can see last year, these are your seniors, who have made us proud, who have made their parents proud, who have made their schools, institutions proud. So, these students, after completing the syllabus, they have watched all the lectures properly and they have also studied through mock tests, analysis, and so many other tools that we have been providing. So make the best use of it. We are here for you because this time I want to make sure that at least 1,000 ranks come from just JEE Enthuse alone. And are you ready for this? Are you ready to take up this challenge? If you are ready, put it up in the chat box, and if you are watching this lecture in the recorded way, put it up in the comment section so that I know you guys are ready to battle it out, because warriors, it's time to get battle ready. So let's get started. Hello Stravana, hi Jajit, hello Nikhil, looks like you are on fire. Ramya is also fired up. Ramya is our young warrior. Very true, very true. Okay, let's get going, my warriors. Okay, so Nizat, I'm so glad that you will be completing all of this from me, and you got this lecture on time too. All right, let's get started. A quick recap of what diodes and PN junctions were. Remember, a diode is like a one-way valve which allows the current to flow only in one direction and blocks the current in the other direction. When it allows the current in one particular direction, all right, so that is called as the forward bias. Reverse bias is when it blocks the current. So P type and N type, they are merged together. They form potential barriers. P has more holes, N has more electrons. Recollect, there is diffusion current, drift current, and when the forward bias is active, the diffusion current overtakes the drift current, and that's why the current circulates in the circuit because, you know, of this particular diffusion. And in the reverse case, when it is opposing, that is in the reverse bias, you will see hardly any current is there. It's like completely blocking the current whatsoever. Alright, so this is a symbol of diode. This is how an actual diode looks like. This is the construction of the diode, what is there inside, P and N type. Okay, and this is the symbolic way of how you're going to represent it in the electrical circuits. This graph, do you remember it? Ankit, I have explained the PN junction in my previous lecture. If you have not watched it, please watch the entire video, bacha log. It's all there over here. Okay, in case you do not know where to find it, I'll just show you. It's there over here. Just go to playlist tab. Okay, just go to the playlist tab and go down to the Pathfinder physics playlist. Okay, and just probably you can also click over here. Okay, so that's it. I don't need this now. It's there right at the bottom. Okay, so you can just go at the bottom. You will see Semiconductor Lecture 1, PN Junction Diode. A big lecture. You need to understand it from the basics, just in case you have missed it. Okay, I'm very good, Abhishek. Thank you so much. Okay, is that fine, Ankit? You will be able to watch that. All right, cool. So let's get started and let's move on to the IV characteristics. This is also yes, I have done in lecture 1. Yes, I have done the lecture 1, Ankit, long time back. I mean last week or something. Okay, and this is the IV characteristic, current versus voltage characteristic curve. Look at this, how the current changes with voltage. When voltage is positive, it is forward bias. You can see there is a lot of current flowing in it. Okay, and it kick starts only after a certain voltage because it has to overcome that potential barrier. So for an ideal diode, there is no barrier. But for a real diode, there is some barrier, after which only, you know, the conduction begins very rapidly. And remember, in the reverse bias, you can see hardly any reverse current is there. That is negligible, unless and until a breakdown occurs, but that is for a very high reverse bias voltage. Okay, so that is for a large amount of reverse bias voltage. Will that, you know, the reverse drift current, you know, break in, and you will see a huge surge of current suddenly happening, but that is for very high voltages. All right, so let's talk about the different applications of a diode. Trust me, diodes have changed the, you know, a whole scenario of our 20th century. And do you know something which is going on right now? There is a shortage of semiconductors. Yes, there is a huge shortage of semiconductors right now which is going on because of so many things, of the sudden surge in demand and lot of, you know, ships and trucks which carry these devices from different parts of the world. Because of the lockdowns and so many, you know, transportation issues, they are not able to reach the factories. So there are so many equipments which are not being able to manufacture because the semiconductors are not reaching it. And maybe you would have seen this in the news, or if you have gone to buy something, maybe a television or even a car or even, let's say, some computer, you will probably see the older models are there. And you know, be very careful this year. Even if you have bought the TV or any fridge or washing machine last year or something, most likely they would have sold you the 2020 model or 2019 model. And what they do is, because they know customers are also smart, what they do, they just change the outer cover and they just make some small plastic refinements, and then they will tell you this is the new 2021 or 2022 model. That's crazy. Yeah, so you be careful because the specifications internally have not yet changed. Very few companies have been able to manage, you know, that sudden surge of demand and all of that. I remember I had faced so many problems when I bought my electronic devices out there. Yep, it's crazy. All right. So anyways, so I'm pretty sure eventually it will catch up, but that's something which you should be very, very careful about. Oh my God. Yes, Ankit also agreeing with this. You bought a TV and they sold a 2022 model. Trust me. And I heard the news saying where, you know, they are selling cars without many of the features inside the cars. So many features, because semiconductors are needed in so many digital gadgets inside your new generation cars also. So they are like, okay, we don't have these features because there is no semiconductor. We'll sell you the older model, or we'll not give you that, you know, feature itself. You come later on and we'll give you that feature. We'll fit it later on. It's crazy. Anyways, light emitting diode, LED. Have you seen an LED? You would have seen it definitely. So many places. Okay, in switch boxes, boards here and there. It is like an indicator. It is like an indicator. It looks like this. It can emit different colors, and the way it works, okay, and the way it works is basically in this diode. All right, when the electrons flow and when they fill up the holes, the electrons jump into the orbits of the atoms. And do you remember atomic structure? Do you remember atomic structure? Yep. In atomic structure, you would have learned that, you know, when electrons enter from higher orbit to lower orbit, they emit photons. So that's what happens in a LED. It so happens that when the electrons fill in the holes, then they complete or they go to a lower energy state, and that's when you will see the emission of photons. If those photons are in visible range, you can see it. So you need to make sure that the transition of the electrons from higher energy state to the lower energy state, when they jump and fill into those holes, are in the visible spectrum. Yep, they will emit photons. So very, very important and very, very interesting. So if you're wondering how the diagram of LED looks like, so it should be shown symbolically something like this. Because it emits light, so you show two arrow marks coming out of it. That is nothing but a LED. Long time back, we used to have LED TVs. Your TV screen used to be made of these LEDs, red, blue, green, so many LEDs, small, teeny, mini LEDs. So that was your LED TV. It's a matrix of so many thousands and millions of LEDs. It's crazy. Amazing. Oh, Shri Harshit, you can learn from both places. Yep. So nowadays we have OLED and plasma and God knows what. Yep. Yes, Nikhil, that is radiation. What you're talking about is radiation. That is thermionic emission. We are talking about emission due to, change in the orbits. Okay. Yep. So Uma, we already have a crash course which is running for, 8,000 bucks. It's there in the link in the description box below. So you can join that. On YouTube, we'll be having different kinds of other courses like sprints, mock test, and stuff like that to support the crash course. Because doing the exactly same thing does not make sense if it is already running as a crash course. We'll be doing something to assist the crash course which is running inside our Vedantu app. Alright. Now the next thing, photodiode. This is exactly the reverse of the previous one. If you have visited some nice hotel, and I used to always get scared and fancied at the same time, in these hotels, when you go near the wash basin and try to wash your hands, you don't even have to open the tap. Automatically the water comes out. And the way it works is using a photodiode. So a photodiode is where the conduction begins, or the conduction is hampered, or it is controlled by the amount of light which is falling onto it. The amount of light which is falling onto it. Yep. Yes. So it's crazy. And the symbolic way of showing it is the exact reverse of a LED. Show the arrow marks falling onto the diode. That's it. That's a photodiode. So what happens when light falls on that PN junction diode? You will see the energy of the electrons affects the conduction of the current in that PN junction diode. So the light controls current indirectly, and that current helps you trigger different circuits, and that can open, close many things. So that's how your automatic wash basin works. Have you seen one of them? Very good, Abhishek. I'm so glad you used it, and now I'm pretty sure your entire 11th standard revision will be done in an awesome way. All right. So this is how, or this is one of the another application of a diode or a PN junction, diode. Crazy. Okay, I'm so glad, Anirudh. I'm so glad. I'm pretty sure you will stay with me till your 12th standard, and I don't know, you will probably crack your JEE 2025, 26, with me too. All right, thank you so much. Okay, next thing, Zener Diode. Now, Zener Diode is a very special diode because the manner or the way in which it has been used and constructed. So this is how Zener Diode looks like practically. Okay, this is a very tiny mini thing, and this is a symbolic way of showing into it. Remember Egyptian dance, they do like this, right? So this is like Egyptian dance. So this is the symbolic way of showing Zener diode. Remember Egyptian dance. So normal diode has a flat thing over there. You just bend those two things. That's the symbolic way of representing a Zener diode. Now the manner in which Zener diode is used is always in reverse bias. Because that's a special application, and it is used for controlling voltage. Yep. Have you seen or worried about suddenly the voltage increases in your house or apartment and you are worried, oh, what if my charger explodes? Oh, what if my battery explodes because I'm charging it in some way? So this device helps in preventing voltage surges. Many of you did not know this, so now I'll explain how this works. Yep, very good. Okay, very good. Very nice, Abhishek. You got my HC Verma and derivation lectures. Very good, very good. I'm pretty sure you'll make full use of it in this 1 month. Make full use of it. Now, how does it control the voltage? Okay, this is a circuit. I'll explain it to you by drawing on the next slide. But before going to that, I want you to remember this particular IV characteristic graph. Forward, reverse. Forward is not important, reverse is important for Zener diode. Remember, this Egyptian dance happens. You should imagine somebody doing this Egyptian dance in reverse mode. Okay, they are going behind, reverse. Imagine an Egyptian doing this dance and going behind. That's how you're going to remember this. Okay, this is the important part. In the reverse bias, there comes a phase where the breakdown happens. And in that breakdown, you will see the voltage becomes constant. The voltage becomes constant. That's what is very, very important. So I'm just going to go over here and I'm just going to help you with this. Okay, now let's go over here and draw a circuit which will explain, which will help you understand how this Zener diode becomes like a voltage regulator. Okay, great. Okay, so imagine this is your Zener diode, okay, like this, Egyptian, and it has to be connected in reverse bias. So this ideally should be positive, this should be negative because it's in reverse. The upper one is positive, the down one is negative. So let's say this is connected to the negative terminal, and this, let's say via some battery, or sorry, via some resistor or something, it is connected to the positive terminal. This side is your input side. This side is your input side. Okay, this is the negative and this is the positive terminal. And what I do is I take out 2 more terminals from here. And this is something which I call it as the output. Now, imagine this Zener diode is specified as, imagine the breakdown voltage. The breakdown voltage of a Zener diode. For example, let's just take some example. Let's say it is, I don't know, maybe 4 volts. Imagine, it's given. That means what happens is, in this graph, no matter what you try to do, the voltage, okay, the voltage remains fixed to 4 volts in the reverse bias mode. In this current versus voltage graph, after the breakdown occurs, the voltage does not exceed 4 volts in the reverse bias, no matter what you try to do. Yeah, the voltage remains constant. This is negative voltage, 4 volts. So no matter what you try to do, the voltage cannot exceed beyond that 4 volts. That is a specific example. Some another Zener diode might have 100 volts as, I don't know, breakdown voltage. Some another diode might have 7 volts as breakdown voltage. So every Zener diode, depending on how it has been made, will have different amounts of breakdown voltage. Everybody clear till this point? Yep, it will help in computer applications. Yep. So yes, you will get many LT replays, Sri Harshit, is the long-term batches replays. So that's the advantage. So you can get the long-term batch which has happened entire year. Last year, all those replays are also available to you free of cost when you join the 1 month crash. That's what is it. Okay, Sri Harshit? Okay. Now, Imagine that the input voltage, I'll just give you some examples. Let's say the input voltage is 2 volts, then it changes to 3 volts, then it changes to 4 volts, then it changes to 5 volts, then it changes to 6 volts, then it changes to 7 volts. Examples. What will happen on this side? Okay. The moment the input voltage exceeds the breakdown voltage, you exceed the breakdown voltage, no matter what you try to do, you cannot have a voltage drop of more than the breakdown voltage, in this case 4 volts, under any circumstance. That means the output voltage, after this will always be 4 volts no matter what you try to do. You'll be like, okay, great. So if I give 5 volts, still the output is 4 volts. If I give 7 volts, still the output is 4 volts. Then where is the remaining voltage getting dropped? The remaining voltage is getting dropped over here in this resistor. So this resistor plays the role of, dividing that voltage between the Zener diode and the resistor itself. So for example, if I ask you, what is the voltage drop across the resistor? When it is 4 volts, it is 0 volts, because nothing gets dropped across the resistor, everything is dropped across the Zener diode. When it is 5, 4 is dropped across the Zener, 1 volt is dropped across the resistor. When it is 6, it is 2 volts. When it is 7, it is 3 volts. If it is below 4 volts, then you are not operating the Zener diode properly. It's quite possible, maybe some amount of voltage, I don't know, maybe 0.5 volts is being dropped over here. Maybe in this case 2 volts is dropped over here. I don't know, I'm just giving you some random examples. Okay, maybe this could be, okay, if this is 0.5, obviously this will be 2.5. If this is 2, this is also 2. I don't know, I'm just saying these are some random values which I've just projected over here. But the point is, the Zener diode becomes operational only after the breakdown voltage. You can see the output voltage remains constant irrespective of the input. The remainder voltage gets dropped across the resistor. Ankit, 4 volts was just an example. Okay, all right. Uma, probably yes, probably no also. Reason is, if you sit and watch all the classes, it will take you more than 45 days, because all these are long classes, number one. Number two, the crash course has been designed in a way that, all the important things are covered in a very systematic flow way, so that you can complete it in 45 days. Number two. Number three, when you watch the one-shot videos in crash or whatever revision plan, and then you need some additional help, then the topic specific detailed lectures you can watch. That's how you should tackle this problem. Okay, so here is the thing. I'll just quickly give a recap so that you guys get this again. This is your variable voltage. The voltage can vary. This is your filtered voltage, which has to be constant. Zener diode is always connected in reverse bias, and each Zener diode will have a certain amount of breakdown voltage. So example, this diode has a breakdown voltage of 4 volts. That means if you try to push the voltage beyond 4 volts, no matter what you try to do, it will not exceed 4 volts. So till it reaches 4 volts, this Zener diode might have some amount of voltage difference, but the moment you exceed 4 volts, if this becomes 5 or 6 or 7, out of those 5 or 6 or 7 volts, only 4 volts will be dropped here, and the remaining part will be dropped across the resistor. So that way it will make sure no matter how high this goes, only 4 is dropped here, or the breakdown voltage is dropped here, and the remaining gets dropped across the resistor. Is that clear? Or you can still go back even in a live class. You can start from the beginning and you can catch up at 2x speed. Trust me, it will work, and you will definitely come over here wherever I am teaching. Okay, fair enough guys. Is that clear? Everybody give a thumbs up if you have understood what a Zener diode is now. Okay, mainly you should understand it is in reverse bias. Number two, you should understand how it is able to control the output voltage. Great. Okay. Now the next thing, this is your adapter which you would have used in your computers or sometimes your mobile chargers and all of that, right? So how does this work? Well, obviously there is some kind of regulator happening in this, but apart from that, this adapter does one very important job, and that is called as a rectification. Rectification means converting AC voltage to DC. Okay, now why is that important? Very, very important. Okay, somebody is already using it, obviously, if you're watching it on the laptop. Imagine you have AC current which is entering into a battery. What is the problem? Put it up in the chat box. Imagine AC means positive, negative, positive, negative. In the positive cycle, it charges the battery. Negative cycle, it discharges. Negative cycle means the current changes the direction. So in one half of the cycle, it is charging. The other half, it is discharging. Charging, discharging. So what's the use? There is no use, right? Hence, you need to convert that AC into DC. And once you convert AC into DC, the current only flows in one direction, and then it can charge the battery only in that particular direction. Is that making sense? Yep. So that's why whenever you have to charge a battery, you always use DC. So the conversion from AC, your mains socket which is there, that power socket, that is always AC. You convert that AC into DC. That's very important, and that job is called as rectification. Okay, all your electric vehicles, they will always need this rectifier, because when you connect your power supply, they have to convert that AC into DC. How many types of rectification and what is the basic process of rectification? I'll just explain it to you. Okay, now you just need to know the basics of it. Okay, just understand the basic conversion principles, and there are two basic types of rectifiers. Just listen in carefully, you will get a feel of this. So there are two types of rectifiers. One is called as a half wave, second is called as a full wave rectifier. Okay, now what's the difference between the two? Okay, just imagine this. This is your input AC signal. Okay, this is your input AC signal. You perform a rectification. So let's say I call it half wave rectification. In half wave rectification, only half of the complete wave will enter inside. Meaning, let's say if this is your wave, AC wave, then you will see only this part, then flat, only this part and then flat. You can see the negative half is not there. When that negative half is eliminated, what has happened? Look at this. In this bump or this bump, the current is only flowing in one direction. Think about it. The other half is, yes, completely eliminated. The current will only flow in one direction. See, what are these halves? What are these halves? Plus, positive and negative half cycle. If it is positive half cycle, that means the current is flowing in one direction. If it is negative half cycle, that means the current is flowing in the other direction. So if the negative half cycle is absent, then the current is only flowing in one direction. But this is not a great rectifier. Reason, the current flows in one direction, then stops. Nothing. Then again current flows, then stops. Again current flows, stops. Don't you think a lot of energy is getting wasted over here? Don't you see that half of the energy just went off because you're not making use of the negative half cycle. The second type, like you would expect, instead of half, you have full wave rectification. In the full wave rectification, it is like a modulus function of this graph. So you will see bumps like this. You will see bumps like this. Understood, my warriors? You will get the entire wave completely transferred to the other side. So this is a better rectifier. This is not so great. But then you will be like, sir, what is the advantage of this? Well, that's cheaper. Okay, so it's up to you. You pay more money, you get better quality. You pay less money, you get this kind of quality. Is that understood? Okay, that's how it works in real life too. All right. Now you will be like, sir, still I do not like this, sir. What kind of DC is this? Obviously, this is DC current. This is DC current, right? Because the current is only flowing in one direction. Sir, the current is increasing, then decreasing, increasing and decreasing. I know it is there only in one direction, but it is still, a bumpy ride. I do not like it. I do not like this bumpy ride. Fine, you don't like that bumpy ride. How do you get rid of that bumpy ride? You do something called as filtering. You do something called as the filtering. And once you do filtering, you will see that the bumpy ride becomes something like this. Almost roughly a constant. Anyways, you don't have to worry about it right now, but just know this filtering is done so that, you know, the bumpy rides becomes smooth. It's like your suspension, it's like your shock absorber. IGT, I'm very good. Please rewind back the session and catch up at 2x speed from wherever you are. Okay, chalo. So let's see a half wave rectifier now. All right, a half wave rectifier. So what is a half wave rectifier? I'll show you, and we'll make use of a diode for doing this. Remember, if you have a diode, okay, and if you send in current like this in forward bias, you will see it will definitely conduct. Okay, it will definitely conduct. If this is positive, this is negative. But if you connect the same diode in a reverse bias, that means if you make this positive, this negative, so this is reverse bias, so it will not conduct. It will definitely not conduct. Now, this principle can be used for making a half wave rectifier. You would have slightly got some idea. Oh, there is a positive cycle, negative cycle. Once the current is going like this, then the current is going the other way around. So when the current goes in a particular way, the diode will conduct, and when the current reverses the direction, the diode will not conduct. Hence, you will get a half wave rectifier, something like this. Observe, this is the input side. This is the input signal. Okay, so these are the positive halves. I'll just mention over here. Okay, this is your positive halves, and this is your negative halves. This is basically your input side. Now, in the positive half, the current is flowing clockwise. You can observe this. This is clockwise. This diode is forward bias, and that's why it is conducting, and that's why you can see the current also increasing and decreasing in the same way. So it is basically conducting. It is conducting. That's what has happened. Oops. Okay. Let's see. Yeah. Okay, great. Now, in the other half, the negative half cycle, the current reverses the direction of the flow. That means it wants to flow like this. And in this case, obviously, it is in reverse bias. And the moment it goes into reverse bias, you will see no output. And that's how you get a half wave rectifier. So if you combine both of them, positive, negative, only the positive cycles will come out, the negative cycles will not come out. So that is your half wave rectifier. Is that clear? Clearo? Understoodo? Let me know in the chat box. And you can see this beautiful simulation out here which has been made. Okay, just observe this, 1 second. Yep, you can see that. So this is the positive half cycle, the diode is conducting. The negative half cycle, reverse bias, it is not conducting. Yep. How reverse? Because in the negative half cycle, the polarities are reversed. The polarities are reversed, Ankit. So the polarities are reversed, the current will try to flow in the opposite way. Look at this. In the negative half cycle, you will see that, you know, it will not conduct anything. That's it. It's stopped. Okay. So this is the input. This is the output. Very, very important graphs. Clearo now, everyone? Is this clearo? All right. Shall we move ahead? Okay. Next, full wave. Full wave rectifier can be made something like this using something called as a center tap rectifier. Transformer. This transformer is called as a center tap transformer. The meaning of a center tap transformer is, simply put, you know, in a transformer, what do you have? You have the primary winding. Remember that? You have the primary side and you have the secondary side somewhere over here, correct? Like this. Now, usually what happens, this is how your transformer looks like. But what if from the middle I take one more wire? From the middle I take one more wire and I consider either this as the output, I consider this as the output, or I consider this as the output. I have two outputs, output 1, output 2. So basically a primary has given birth to two secondaries. So I can take the output from this secondary also, or I can take the output from this secondary also. Because I'm splitting the transformer right from the middle, that's why it is also called as center tap. You are tapping at the center and taking out a wire to create two different outputs. Is that clear? Understood? Hi Sai Ganesh. Great. Now here is the thing. What you do, because this is a separate cycle or this is a separate output, AC output, and this is a separate AC output, that output is now input for the diodes, but now you make use of two diodes. In the previous situation, what was our problem? In one cycle, one diode was conducting, in the negative cycle, the diode was not conducting. How about bringing another diode which becomes conducting in the negative cycle? Think about it. I'll just repeat. In the previous half wave rectifier, only in the forward bias it was conducting, negative cycle it was not conducting. How about bringing another diode which becomes forward bias for that reverse cycle or that negative cycle? So that's what has been done over here. Observe now carefully. In this positive cycles, you will notice in this positive cycles, this will become positive, this you can assume it as 0 volts, and this you can assume it as negative volt. Or if you don't like it, think of it this way, okay? If this is the positive half cycle, if this is 0 volts, this is some positive, this is more positive, relatively, okay? This is more positive because the voltage will change gradually from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 volts like that. So this much will be 5 volts, this will be 5 volts, totally will be 10 volts. Is that making sense to you? Okay, cool. Now, if this is more positive and this is less positive, don't you see that this one over here will be forward bias? This one over here will be forward bias. Can you see that? This diode and this diode, look at this. This is positive. This is relatively less positive. That means this diode is obviously reverse bias in this case. Hence, this diode will conduct, this diode will not conduct, and once this diode conducts, you will see this side will, the current is flowing from B to A. Can you see that? The current is flowing from B to A. It flows like this. This diode is not even in the picture. Everybody clear till this point? Let me know in the chat box. I need to know if you guys are still there and you are getting it. So in the positive cycle, what has happened? This is more positive, this is less positive, this is 0 volts. Reference. You can take anything as 0, guys. It really doesn't matter. So this diode becomes this diode becomes forward bias because this is positive, this side is negative. So relatively. So hence it becomes forward bias, this blocks, and the current flows from B to A. Now, what happens in the negative half cycle? Observe. In the negative half cycle, look at this. This becomes, let's say, 0 volts. This becomes positive. This becomes more positive because the current has reversed the direction of the current. So that case, this diode becomes forward bias. This becomes forward bias. And look at this. If this is positive, this is 0. The current can't flow like this. Diode blocks the current. Hence, you will see that this diode will be now a reverse bias. Now you can see what will happen. If this diode is forward bias, the current will again flow from B to A. So, what does it tell you? Be it positive cycle or be it negative cycle, the current in this particular device or this resistor or between these 2 points always flows in the same direction. Hence you get the bumps in the same direction, and hence it's a full wave rectifier. This is basically a full wave rectifier. Everybody clear about this? Got it? Clearo? Understoodo? Let me know in the chat box by writing clearo or understoodo. Let's move ahead then. Cool. Now, by the way, this will be how the input and output characteristics graph should look like. This will be the input graph. This will be the output graph. Obviously, it's like the modulus function. Okay. Now, there is one more way. There is one more way of creating a full wave rectifier. That's also crazy. This is called as a bridge wave rectifier. How many of you know this bridge wave rectifier? Let me know. Okay. Now, what is this bridge wave rectifier? See, in the previous one, you used a central tap kind of arrangement and you made sure that you had these two diodes which will make sure that the entire wave passes on to the output side. There is a much simpler way of doing this using 4 diodes, and I will show that to you. Observe this carefully. imagine this is your input, this is your AC signal, okay, this is coming something like this, and I make sure that during the positive cycle, so this is your positive cycle, this is positive, this is negative, the current enters this diode, forward bias, comes like this, goes over here to some device, comes out of it and goes to this diode and again comes out of it here. So there is some device over here. Let's say I call these points as maybe A and this is B. So in this particular positive cycle, this is your AC signal, the current flows from this diode, goes into the device at point A and it comes out at point B and goes through this diode. Both are forward bias. Now in the negative half, when this is negative, this is positive, then the current will flow from here and it can't go in this diode, correct? Because this diode is reverse bias. So how about making a diode here and then let the current go like this and in over here, again from A to B, it comes out at B, but now it can't go here because already the current is coming in here. So it goes like this into this diode, which is also forward biased, and goes out like that. So in this case, you will see during both positive as well as the negative half cycle, you have two diodes which ensure the current will always flow from A to B. So if the current always flows from A to B, be it positive or negative half, that's a full wave rectifier. Crazy, right? Look at this. So quick recap, in the positive cycle, the current reaches here. It can't go here. Why? Because this is reverse bias. This is forward bias. It goes like that and it goes here at point A, goes into some device, comes out at B and comes out like this. Why can't the current go here? Because this is still in reverse bias. In the negative half cycle, the current comes here. It can't go here, it has to go here. So once it goes here, it goes from A to B, it can't come back here. So it will go here and come out like this. The reason why it can't go here is because this is reverse bias. So that's why the current won't go there. Crazy. So this is a bridge wave rectifier. And you can see the simulation of this. Positive cycle, look at how the current is going through D1 and then this D2. During the negative half cycle, observe this carefully. Observe this, during the negative half cycle, what would have happened? Now this complete simulation is not there. Then you would have seen that the current will go from here, come out like this and again come out like that. So it's a crazy arrangement and that's why it's called as a bridge wave rectifier. Okay, Lakshit, fine. I think your name out there is written down as Ramya, so it's confusing at times. Here is your first question coming up on your screen. A Zener diode having breakdown voltage equal to 15 volts is to be used as a regulator in the circuit as shown. Then the current through the diode is... Okay, no problem, Sai Ganesh, definitely. So let's see how many of you can solve this question. And if you feel that this question is difficult, let's solve it together. A Zener diode which has a breakdown voltage, remember that's a max voltage and you cannot exceed it, is used as a regulator. You can see that the input voltage is 20. If the input voltage is 20 and the Zener diode has a breakdown of 15, that means it is now in the on state. It's now activated. So no matter what you do, even if you apply thousands of volts, this Zener diode will be like, no, sorry boss, I will have a voltage drop of only 15 volts. Okay, so you will notice that between these two points, you will have exactly 15 volts, no matter what you do. Now, if these 2 points have 15 volts, obviously these 2 points also have 15 volts because this point and this point, this point and this point is the same, right? So even this entire resistor will also have a 15 volt of difference. Input voltage is 20. 15 volts is dropped here between these 2 points. So remaining 5 volts, where is it dropped? Isn't it obvious? Out of 20, 15 was dropped there. So remaining, where is it dropped, my warriors? Think about it. Obviously, it should be dropped over here. So 5 volts is dropped here because 5 plus 15 is 20. Makes sense? Everybody, my warriors? Clear till this point? This is the initial crux of the problem. Without understanding this, you cannot solve the problem. The question is, what is the current through the diode? Now I don't think I can find it directly. I think I need to play around with all these variables out here and this circuit out here. So let's start with it. I know for this 1 kilo ohm resistor, the voltage drop is 15. So I think I can find out how much current is flowing in this part. So how much current is flowing in the 1 kilo ohm resistor? So for the 1 kilo ohm resistor, okay, here is what I can say. V is IR. So using V is equal to IR. V is 15. I is, I don't know. R is 1 kilo. So 1 into 10 to the power 3. So therefore I1 will be nothing but 15 into 10 to the power minus 3. This is 15 milliamperes. So I found the value of I1. But the question is to find the current through diode. Okay. If I find the current through this resistor, I know by Kirchoff's current law, junction law, I can find the current through the Zener diode. So let's try that out. For the 250 ohm resistor, so for that 250 ohm resistor, V is again IR, voltage is 5, current, well, let's just call it as, let's say, I. So I into 250. So I will be 1 by, or rather 5 by 250, which is nothing but, 5 5s are 25, so this will become 50. Is that correct, my warriors? Now, observe this. 1 by 50, 1 by 5. Come on, guys. How much will this come out to be? This will come out to be 20 into 10 to the power minus 3, which is nothing but 20 milliamperes. Everybody with me till this point? Everybody with me till this point? Now what next? There's only one thing left. If I know that this is 20 milliamperes, this is 15 milliamperes, that means the current through the Zener diode, will be 20 minus 15, which is 5 milliamperes. That's it. Hence, the correct option should be option D. Everybody got it? Yep. It's a simple Ohm's law and Kirchoff's current law problem. This is via Kirchoff's current law. That's it. The only knowledge of semiconductors that you need to solve the problem is for a Zener diode, voltage is fixed in reverse bias. That's all. Apart from that, there is no other knowledge of semiconductors which is required. Okay, let's get going. Oh no, I'm not sure why. I have messaged Sai Ganesh, don't worry. I will just have a word with our admin later on after this. Okay, next question. A figure shows a DC voltage regulator, because Zener diode is used for regulating voltage, with a Zener diode of breakdown voltage of 6 volts. You can see this. It's again in reverse bias. Current tries to flow like that. It's reverse bias. If the unregulated input voltage varies between, this is your input, between 10 to 16 volts, then the maximum Zener current is. Okay, let me explain this to you. Observe, guys. This is your input voltage. It can vary anywhere between 10 to 16 volts. Now the question says, what is the maximum Zener current? If you want to find this value, IZ, that to maximum, that means the voltage which is applied also should be maximum. Got it? So this is input voltage. If maximum current has to flow through the Zener diode, that means in the maximum case, the voltage which is on the input side should be 16 volts. Everybody with me till this point? Great. Next, the Zener diode's breakdown voltage is 6 volts. It's mentioned. That means, let me just remove this. Across the Zener diode, across these 2 points, the voltage drop, because this is 6 volts, across these 2 points, it has to be, what is it? Sorry, not 16, my bad. It has to be 6 volts. It has to be 6 volts. Everybody agrees? So both the Zener diode and this RL 4 kilo ohm resistor, both should have 6 volt drop. No matter what you do, you cannot exceed 6 volts between these 2 points. That is fixed because of the breakdown. Out of 16, 6 is dropped here. Out of 16, 6 is dropped here. Remaining, where will it be dropped? Obviously here. How much is it? Obviously 16 minus 6. So let's do the math. So that's over here. So over here you will have 16 minus 6, which is 10 volts, which will be dropped across these 2 points. Got it? Is that clear? Now start solving the question just like before. If I find out Is and IL, I can find out Iz by Kirchoff's current law. That's it. So how much is Is? I can do that. So using Ohm's law, obviously. So again, I'm using Ohm's law, and I can see V, which is 10, is equal to Is into resistance, which is 2 kilo ohm. So Is will be 10 by 2, that's 5, right? And kilo comes below, which means 10 to the power 3 comes below. This is amperes, so this will be 5 milliamperes. So that's Is. So that's the current through this resistor. Next, through this resistor RL, let's try to figure it out. How much will it be? So through RL, what I'm going to do is, again, V is IR, V is 6 volts, I is I don't know, into RL, that's 4 kilo ohms. Got it? So IL will be 6 by 4, that's 3 by 2, and kilo comes below, that means 10 to the power 3 comes below. 3 by 2 is 1.5, right? So 1.5 milliamperes. So that's IL. Great. I know Is, I know IL. I think the only thing left out here now is to find out Iz. So by using Kirchoff's current law at this particular node, this particular junction, Iz should be this input current minus whatever is being thrown out there. So basically Is is equal to Iz plus IL. Therefore Iz will be Is, which is 5, IL, which is 1.5. So this will be 3.5 milliamperes. Is that there? Yes, option A is there. Yes, Abhishek, I am, bacha. Yep, I am. All right. Great. But my batches had started already before. So, yep, that's how it is. My new batches will be also starting very soon. Don't worry about it. Okay, so that's the answer. Let's move on to something called as the transistor. Cool. Is it enough for 2026 aspirant? I have finished thermal fluids, electricity, gravitation. I'm doing strong on thermal and model. Is it enough? For now, Ramya, yes, you're doing a great job. Enough. Yep. But yep, I feel that for the next year and next to next year, when we'll be giving more Olympiads, you should prepare other topics as well, slowly. Okay. So for this year, yep, it is good. For next year, you can start with more topics like mechanics and obviously electromagnetism. Okay. I'll definitely let you know, Abhishek, as soon as it comes out. Definitely. I'll let you know. Okay. Because you're already a part of Pro, you will be able to enroll. Don't worry. Okay. Now, going ahead to transistors. This is also a very important device. And again, the entire electronic industry is revolutionized because of the transistors. This is how transistors look like. They look like aliens with 3 legs trying to invade Earth, right? Probably from some sci-fi movie. Okay, now the weird part about the transistor. What's the weird part? Come on, you should be able to tell me. It's not tough, Rudra. If you learn under me, trust me, it's not at all tough. What is the weird part? The weird part is that usually your devices had 2 terminals, be it inductor, capacitor, battery, switch, everything. This has 3 terminals. So connecting it is a tricky thing and you need to learn it. This is Siva, this is the last chapter of, second last chapter rather, of 12th. So what is a transistor? It's basically 2 PN junctions together. Okay, here is how it looks like. Observe. You take a silicon wafer. Everybody has those wafers which you get in bakeries and some mart. Yeah, this chocolate wafer, strawberry wafer, God knows what and all you buy. So you buy a silicon wafer. And on that silicon wafer, one side you dope it as P, some part you dope it as N, and some part you dope it as P. Meaning you create some holes by adding some trivalent impurities. So this becomes the P side. You add more holes here as well. Okay, this also becomes P type, and in between You dope it with N type of material, that means pentavalent impurity, something like this. These are your electrons. Alex Gamer, this is an English channel, so we'll be talking only in English. We have Hindi English channel as well, Vedantu JEE. Please feel free to join the channel. In fact, if you love learning in Hindi, you should definitely consider joining the Hindi channel that we have on Vedantu. We have all the options. Yes, Rudra, they're used to amplify, they're used as a switch, they are used to, for so many things, for storing data, for logic gates, so many applications are there. Now, the moment you do this, I hope, if you cover this side, you see one PN junction. If you cover this side, you see one more PN junction. But there is a catch, okay? The amount of doping that is done is not systematic or not same. It's not symmetric. It's different. The sizes are also different. This one over here is very thin, very thin. This one is large, okay? This one is, I would say, nearly large, okay? Nearly large, but slightly less than this side, okay? Now, what you do next is the amount of doping, that's also very important. This one, okay, you dope it by a lot of amount. So there is a lot of doping over here. There is most amount of doping, most doped over here. This is moderately doped. This is moderately doped. And this one, this N or this middle part, you dope it, you adulterate it, you add that impurity by a small amount. So small doping over here. Small doping over here. Now you can do the exact other way around. You can make this N, this P and this N. That's also okay. This type of device is called as a PNP transistor. PNP transistor. If you dope it as NPN, then it is called as a NPN transistor. Is that clear? Understood? Okay, fair enough. Now you would have also seen that there are three terminals coming out of it. Three terminals coming out of it. One from here, then obviously one from here as well, and another coming out from here. The middle one, which is very lightly doped and it is very thin, that is called as the base. What is it called? It is called as the base. The one which is heavily doped and one which is decent in size, that is called as the emitter. Okay, it is called as the emitter. And the one which is big in size but not so much doped as this guy, that is called as the collector. Very, very important. Emitter, base, collector. Doping means adulterating it, adding impurity. You dope something, that means you are contaminating it by something. So a silicon wafer has only silicon atoms, right? You add aluminium, so it is a trivalent impurity. It makes it p-type semiconductor. You add phosphorus into it. If you add phosphorus, it has a pentavalent impurity that makes it n-type of semiconductor. That's the meaning of doping. That means you are contaminating it. Okay, you are making it impure. Is that clear? And you should watch my previous class, Alex, Rudra. Yep, watch my previous class, lecture 1 of semiconductors. I have taught everything about doping, what is p-type, what is n-type, what is hole, what is electron, what is p-n junction, etc. What is drift, what is diffusion. Everything has been taught. Please watch that class. It's there on this channel itself. Next, the way or manner in which you represent this entire thing is also very important. Okay, notice this. So the transistor, the way you represent it is show it like this. You can put it inside a circle also. Okay. Now this one obviously is base. Let's say one is emitter, one is collector. Okay. Similarly, okay, now you will be like, sir, how do I show NPN and how do I show PNP? Okay, there is a very simple trick and I will show that to you on the next slide. Observe. So this is NPN transistor where you have N, P and N is on, sorry, the P is on the middle part. All right. This is your PNP transistor the way you represent both of them, observe this. For NPN transistor, make sure you show an arrow mark which comes out from the base to emitter. But for a PNP transistor, you show the arrow mark which comes inside from the emitter to base. That's the only way you can distinguish between NPN and PNP. So in NPN, the arrow mark comes out. In PNP, the arrow mark, the symbol for it, you will see it inside. That's something which you should know. Okay. So in this case, if you notice, this is a PNP transistor. So for a PNP transistor, what should happen? It should come inside. So if it has to come inside from the emitter to base, you will show it like this. Is that clear? Oh, understood? Oh? Great. So for NPN and PNP, the distinguishing factor between the symbols is only the arrow mark. If the arrow mark comes out, it is NPN. If the arrow mark goes in, that is PNP. That's all. That's all. Okay. Okay. So Bindu, I cannot vouch for any other coaching material, bacha, because from what I have seen, there are very few coachings which give very good quality materials, but I can definitely vouch for the Tattva material. It is very good, obviously, because of all the kinds of problems. And I'm not saying this because I'm in Vedantu, but I have seen so many materials from, including the institutes that you are saying. I'm not really happy with the kind of problems that I have seen in so many other institutes. There are very few coaching institutes which give very good quality problems with vast variety and all kinds of difficulty with solved examples and summary notes. And you know, it's also important that students should be given exactly what they require, not something what is not required also. That's what it is. Okay, cool. So the last thing that I would like to mention over here before going ahead, remember, it's always the arrow mark which is going to come between base and emitter only. You will not show the arrow mark between collector and base. Very, very important. Keep this in mind. Whenever you show the symbols, always show the arrow marks between base emitter only, nothing else. Okay, so I'll just mention it over here. This is basically out. This is basically in. Okay, great. Next thing, that is, how do you connect a transistor? That's very important. There are multiple ways of connecting a transistor because it has 3 terminals. Because a transistor has 3 terminals, how do you connect it? That's very tricky because your other devices, be it battery, be it resistor, be it switches, they all have 2 terminals. So every time you include some device, they will always have even number of terminals. This has odd terminals. So what you do, you take out one terminal common. You take out one terminal common and connect it to 2 different circuits. Example, imagine this is your transistor, okay, something like this. What you should do, let's say this is your base, this is your emitter, this is your collector. Let's say the collector part, I'm dividing it between 2 circuits. I'm taking it as common. This is one circuit and this is another circuit. You can see that the collector is common between this circuit and this circuit. This is called as a common collector configuration. Common collector. Collector is common between these 2 circuits. Is that clear? Okay. Let's try this out with some other configuration too. Example, let's say, again, let me just show the transistor, maybe like this now. I'm going to make the base common between the 2. I'm going to make the base common between the 2 circuits. So from the base, I take out 2 wires and one wire goes here and the other wire goes here. This will be basically your common base configuration. As simple as that. Next thing, let's say for example, I want to make the emitter common. No issues. So this is our emitter. Okay, let us draw it. This is your base, this is your emitter, this is your collector. From the emitter, you take out 2 circuits, one over here and one over here. This is basically your common emitter configuration. This is your common emitter configuration. Now, in all these things, please understand, although I have shown wires, it does not mean that there is actually a wire. You could have your devices in between. You could have your batteries, you could have your resistors, etc., etc. So these are not just wires. Don't have a wrong impression. You can have your resistors, batteries, etc. in all these configurations. Very, very important. Keep this in mind. Okay. So these are the three different ways, and the only three ways you can connect a transistor. Where you take out a terminal, the terminal which is taken out common, that becomes the mode in which you connect the transistor. As simple as that. Okay. Now, is there any chance that you can fail in transistor, Rudra? If you study properly, you will definitely not fail. Okay. Yes, definitely, Durga, it will help you for NEET as well. And yes, Indu Kanan, you can definitely watch even if you are a repeater. In fact, it will be very helpful. I'm pretty sure you have a lot of time as well. Look at this animation, because this animation is going to help you understand the working of a transistor. You'll be like, sir, how does a transistor work? Okay, you showed this is how it is constructed, this is how it is doped, this is how the impurities are, this is how the sizes are. But okay, how do you make it work, and how do the currents flow? What's the direction? Which one is more, which one is less? So for that, I am putting forward this simulation. Keep this simulation in mind, because this will help you understand the entire working of a transistor. This side over here is the base, this side is the emitter, and this side is the collector. Now why am I saying this? You will understand. Hold on for that. But let me mark over here first. This is your base, collector, and this is emitter. So what happens is, you can see that this gate is somehow connected via a lever to this another gate, and there is water flooding in this canal, and the moment you trigger this gate and it opens, the water enters into this canal. This is connected to this gate opens up, the water in this part also starts flooding this canal, and both the streams join over here and flood this particular part. It's crazy. I want you to remember this simulation, because I'll come back to this simulation and then you'll understand it better. Why is this related to base, collector, and emitter? This is very, very important. So, going back to the transistor diagram, we can take any transistor. Let's say here in this case we have taken an NPN transistor. Now, observe carefully. In N side, obviously you have a lot of electrons, so I'm showing it as dots. And because it is an emitter, there will be a lot of electrons out here, because it is heavily doped. The collector, although it's big in size, it will not have as much doping as the emitter. So there are electrons, but not as much as this side. And obviously the P type, that has holes. I will show few holes over here. Got it? Now, the most important thing when you operate a transistor is that make sure that your emitter base junction is always forward bias and base collector is always reversed bias. So I'll write it down for you guys. The emitter base junction should be in forward bias to make it operate properly, and your base collector junction should be in reverse bias. Let's see now what happens. When I say emitter base is forward bias, meaning P is connected to P, N is connected to N, correct? So N is connected to negative, P is connected to positive. So that means all you need to do is connect this guy to the negative terminal and connect this guy to the positive terminal. Fair enough. Next, base collector is reverse bias. If this is reverse bias, the base and the collector, if they are in reverse bias, N is connected to positive and P should be connected to negative. Hence, you will connect it something like this. See if this makes sense. Now, this PN junction is in reverse bias. Everybody clear out till this point what we have done? You'll understand why we have done this in a bit. Hold on for that. You'll be like, sir, why did we do this forward? Why did we do this reverse? You'll understand the basic working of a transistor only when you connect it in this particular manner, and the moment you see the flow of electrons, you will understand what that simulation meant and how you can use the transistor as an amplifier and all of that. Fair enough. Now observe this. Because this is a forward bias and this is negative to negative, positive to positive, what's the first thing that clicks in your mind? The negative terminal, and these electrons will obviously repel, correct? So what will happen? These electrons will be pushed away because of this negative terminal. These electrons will try to go this side, making sense? And in fact, these electrons want to merge onto the holes. But do not forget one thing. The amount of holes are very few, number one. Number two, the size of this is very small. Number one, holes are less. Number two, the size is very small. The moment this negative terminal repels these electrons see the holes and they get excited and attack the holes. There is a problem. Very few holes are available for these electrons. Most of them will get filled up, obviously. And what about the remaining negative charges? What about the remaining negative electrons? These electrons don't have space, number one. Number two, imagine it's like 100 hungry kids are there and there are 5 chocolate cakes or vanilla cakes or something placed on the side of the table. Obviously, the moment all these 100 hungry kids will see those 5 or 6, cakes, they are going to pounce on it. Maybe 5-6 students will get that cake. The remaining, because of the momentum, they will spill over on the other side. Correct? They will spill over on the other side. So these electrons which got excited looking at these holes, and these electrons which got repelled by these negative charges, by the negative terminal, because of their momentum, because of their excitement, they will spill over on the other side. They will spill over on the other side. Okay, they are getting spilled over. They are getting spilled over on this side. Some electrons, few of them can see that there is a positive terminal over here. Those electrons will come over here. Very few. Because of the rush, it's like, all the kids pounce on the cake. Because of the momentum they get spilled over, there is a small door opening on the other side. Few kids will exit that door because they don't want to get crushed. So they are exiting and they are seeing that, oh, there is a positive terminal here. Oh, there is a cake kept outside the classroom. Think of this like the classroom and think of this like the door. So the moment they see the door, they get outside the door and they go for that bigger cake out here. But those are very few of them, not all of them. Is that clear? What has happened? So very few electrons will go over here. Most of them will get spilled over, few of them will combine with the holes and all of that. Now you will be like, sir, how can these electrons get spilled over when there are already electrons over here? Then this particular statement comes to use. The base collector junction is in reverse bias. Very, very important. Look at this. Positive connected to negative, negative connected to positive. So these electrons which were coming over here, very few of them, they cannot enter here, number one. Number two, this positive terminal will pull these electrons anyways. Positive, negative attract, right? So these electrons will get pulled over here by this positive terminal. The moment these electrons get pulled, what happens? There is space created over here. There is space created over here to accommodate the new electrons which are getting spilled over from this side. Got it? So basically these electrons which got spilled over, they are occupying those spaces and they are replenishing, they are filling up those empty spaces left by the electrons which have gone to this side. Now what will happen? Once they get spilled over and they will also now start going over here, you will see there is a kind of a flow which is set up right over here. These electrons will come again over here, because do not forget, if all the electrons jump here, then there will be nothing left to jump. So there needs to be some supply of electrons. Where will that supply of electrons come from? It has to come from both these places. So the few electrons from here will combine, meet, and again fill up that stock. They will fill it up. They will fill it up back. And again the same things continue. That is what happens. So that's how a transistor works. Clear? Okay. Now if I talk about the current direction, very important. This is the flow of electrons. Current will flow exactly opposite to the flow of electrons. That means if the electrons are coming like this, the current is flowing like this. because it is entering inside the base, this is called as the base current. Because the electrons are going like this, the current is flowing opposite, this is called as the collector current. And electrons are going like this, that means this one coming out of the emitter is called as the emitter current. Everybody got it? Exactly opposite, nothing else. And you can see by Kirchoff's current law, the emitter current is getting distributed into two currents. Hence, the emitter current is basically the base current plus the collector current. This is one important statement. Very, very important. Good? Clear? Next statement, which is important. The emitter current is very large and it's comparable to the collector current. The base current is very small. Why? Because very few electrons will leak out from this side. So usually the base current is very small as compared to the collector or the emitter current. Very important point. Keep this in mind. That's the reason why I would then say the emitter current, which is base plus the collector, since base is negligible, it's almost equal to the collector current. Keep this in mind. Everybody understood? Bindu, you can solve numerical problems from DC Pandey, you can solve from Tattva, you can also solve it from, PYQ series of Arihant, you can also solve it from, Erodov, you can also solve it from H.C. Verma. All these are good sources for solving physics problems. Okay? Cool. Now, let's also have a look at the parameters which are there for, yes, transistors. Many of you would have seen or heard about the parameters which are involved in case of transistors, alpha and beta, very important parameters. That's going to tell you the relationship between the base, collector and the emitter current. So those parameters are called as the current gain parameters, and there are two parameters which define the relationship between these variables. What are they? As simple as that. They are nothing but alpha and beta. What are they? They are alpha and beta. Now, how has it been defined? Look at this. Alpha is equal to, beta is equal to, always put collector on the top, collector current, collector current. Why should you put collector on the top? Simple. This is how you're going to remember it. Collector is a government post. Collector is a very big post. It's like a government official. And where does a big government official sit? He'll sit on top of everybody's head, right? He's going to sit on the top, he's going to sit on the chair, and he's going to go command everyone. So, C, collector, okay, will be a top position, top government position. So, hence, it will be sitting in the numerator side. At the bottom, which current will come? How will you remember it? It's very easy. If it is beta, beta B stands very similar, right? So this will be base current. Naturally, the only variable left is emitter current, so this will be IE. That's it. That's how you're going to remember these two parameters, alpha and beta. They will give you these parameters and they will expect you to solve some numerical problems based on this. Very, very important. Okay. So alpha and beta gives you the relationship between the base, emitter and the collector current. These will be given to you or they will be asked to find out based on other pieces of information. Cool. Shall we move ahead? Okay. Let's solve some questions based on this. Did I feel any topic was hard? Yes, I did feel many topics were hard when I was preparing for my JEE, and it depends from person to person. So there are always some strengths and there are always some weak points, definitely. So you need to make sure your strengths are very strong, that they will fetch you marks, and your weak points are at least done till a specific level so that you are able to solve at least the average questions on that. Okay, cool. A transistor, the width of dash is more than dash. In a transistor, whose width is more than whose width? Well, if you've forgotten how to solve this, let me go back over here and I've mentioned it right over here. Look at this. The collector is the largest, the emitter is next, and the thinnest is the base. So who is larger than whom? That's very simple now. Look at this. Isn't the collector region slightly more than the emitter region? Rest everything else is going to be smaller. Is that okay? Cool. Yes, modern man, it will be. Okay. And also, I need to go back to the simulation. Now probably this makes sense because the base current is usually small and the emitter current is base plus the collector current. Now this animation makes sense. This water flowing is very small, but this base current or this base flow controls the net current. You can see this water and this water merges to give you the final water coming out of this emitter. This lever controls the collector current. A small change in the flow here affects the flow of the current in the collector, that affects the total flow coming out of this. Although this water coming out is small, understand that it controls indirectly the large current or the large flow which is the collector. So, this is how the simulation makes sense probably. You can see right over here, a small change in the current over here affects the collector and the emitter current because this is connected to them. You can see that these parameters are defined. For a given base current, beta is defined. If I change base current, you will see the collector current will also change. And if you change collector current, accordingly emitter current will also change because these parameters are fixed for a transistor. Okay. Yes, Srinivas, definitely watch my advanced. How can an average student crack advanced, and what are the different milestones that you must achieve in the days and weeks to come? Watch that lecture, is there on this channel. Definitely you can crack advanced, bacha. Okay. Now, can I relate alpha and beta? Yes, obviously. It's very simple, but don't have to remember any formula. We'll see some questions based on that in the coming few slides. Okay. In an NPN transistor, the collector current is 24. If 80% of the electrons reach the collector, then how much is the base current? That's the question. If 80% of the electrons reach the collector, then what is the base current? Okay, let's understand the meaning of this question. See, you have your transistor over here. Let's say this is emitter, this is base, this is collector. Okay, now what is given is 80% of the electrons reach the collector, meaning out of the emitter current, 80% is reaching the collector, 20% is reaching the base. Got it? Understood? Out of this 100% coming out of the emitter, 20% is reaching the base, 80% is reaching the collector. Because remember, I have told you the emitter current is always the base current plus the collector current. If you remember this simple diagram, that's it, your half of the job is done. Now it's clearly mentioned the collector current is 24. Then the question is, what is the base current? Simple now. What you will do? Because collector is 80% of emitter, the emitter current will be 100 by 80 into the collector current. And that is given 100 by 80. And the collector current is given to be 24 milliamperes, correct? And you might as well write this as 5 by 4 because 100 by 80 is 5 by 4. This will become 6. So this will become 30 milliamperes. That's your emitter current. But I don't want emitter, I want the base current. How do I find the base current from this? The base current will be emitter current, which is 30, minus the collector current, which is 24. Which is 24. Let me just erase this. Yep. This is 24. So this will be nothing but 6 milliamperes. Correct? Is that there? Yep, it is there. Right over here. You can see that. So what was the trick? The trick is just to remember how the currents flow. Number one, draw a simple diagram. Number two, remember the basic formulas. Emitter current is base current plus collector current and alpha beta formulas. That's it. Rest all is simple numerical maths. Is that clear? Or can we go ahead to the next question coming up on your screen? And here it is. Let's solve this. So what do we have over here in the next question? For a transistor, the parameter beta is 99. The value of the other parameter alpha is how much? Very straightforward question, and these kind of questions are very common. First of all, what is beta? Beta is nothing but, remember I told you collector always sits on the top, and if it is B, then you will have base over here. And the next parameter is alpha, and alpha will be again collector sits on the top, But if base current has come over here, you will have emitter over here. So you want to find alpha from beta. Simple. I'll tell you what you can do. Emitter current is nothing but base plus collector. So this is nothing but base plus the collector current. Emitter is base plus collector. That's the standard result. Okay, divide numerator and denominator by IC. So what will you get? 1 divided by IB by IC plus 1. I've just divided numerator denominator with the same number IC. Look at this. IC by IB, that's beta. I want to find IB by IC, as simple as that. So just put it over here. So I'll get this as 1 by 1 by beta. Okay. So this will be nothing but 1 divided by 1 by beta, because this is reciprocal of this, plus 1. So this will become, take LCM, beta upon beta plus 1. So just substitute now. What is beta? It's 99. So 99 upon 99 plus 1. So that's 99 upon 100, which is 0.99. And do I have such a number? Yes, I have it. Right over here. Yes, Sumit Sharma. Correcto. That's it. That's the correct answer. Now, from the previous slides where that animation was shown, you would have realized that by controlling the base current, indirectly you control the collector current, and a small change in the base current can affect the collector current and indirectly the emitter current. And this leads us to an application called as an amplifier. What is an amplifier? Amplifier amplifies the amplitude. It increases the amplitude. Example, I'm using a mic. My voice becomes louder because there is an amplifier in the circuit. Meaning, it takes in my electrical signals. Those signals are stretched. So by the time it reaches the speaker or your headphone, it increases, it amplifies the sound, and that's how an amplifier works, or that's the basic understanding of an amplifier. It increases the amplitude. So how does a transistor help us in amplifying things? This entire simulation should give you a sense of how an amplifier should work. Think about it. Bindu, I'm so sorry, bacha, we cannot give you PDF of Tattva in the Telegram or anywhere else. Best part, all you can do is you can take up the trial and you can see it. Number one. Number two, I've conducted a session on how the Tattva looks like just few days back. Just have a look at it. In that I have clearly shown how Tattva looks like. Just watch that video. Trust me, it will be very helpful. Okay, cool. Now, looking at this, you should probably develop a sense that if somehow this is my input, which is very small, I want to make it big. If I give the input to the base, and if my output is coming from here, you can see that a small change, if I change this little bit, a large change is observed here. That's the whole concept of using transistor as an amplifier. That's all. Got it? I'll repeat. A small change in the wall position here controls the flow in the base that affects the collector and the emitter indirectly by a large amount, and that's how you can get large changes in the flow in the emitter side or the collector side. So that is indirectly amplifying the changes, amplifying the controls over here. So going back right over here, for transistor as an amplifier, you will notice, this is how a transistor as an amplifier works, by the way. There's a circuit diagram. Look at this configuration. This is the common emitter configuration. Common emitter means emitter is common. It's the same terminal is taken on both circuits. In this circuit, this is your input signal. You can see a signal is coming over here. It's fed inside the base. It is led inside the base. Eventually, the other side, the output circuit, okay, you will notice it's fed inside the collector emitter side. If you change the base current by a small amount, you will notice there will be a large change in the current on the output side because it is the emitter collector side. So you will see the amplitude of this guy will be much larger than the amplitude of this guy. I hope this is clear. Everybody understanding this? Everybody clear about this? Okay, so that's how you use transistor as an amplifier. Controlling the base current, you indirectly affect the collector emitter currents, that indirectly affects the amplitude, and that's how you get a larger amplitude. So usually this is connected to your mic, this is connected to your speaker. So that's how the sound gets amplified. The electrical signals get pulled, they get stretched out. Great. There's only one thing over here which you should remember. This input and output, they are out of phase. That there was a question which was asked in JEE Main some years back. So the output is opposite in phase of the input. So if this is negative positive, that will be positive negative. It's exactly opposite. That's one thing you should remember. And the parameters which you should also keep in mind is input resistance and output resistance and all of that. So it's very simple, guys. So for the input side, you can say that the changes in the input voltage will be V is IR, input current, which is in this case the base current, into the resistance of the input side. The resistance of the input side, V is equal to IR. Same way, you can also mention about the output side. You can see that the output is connected to the collector. So the change in the voltage on the output will be the collector current in this case into the resistance of the output. So this is simply put Ohm's law, nothing else. And you also have your alpha and beta gains that you have. So the amplification factor or the current gain, usually what is this? So beta, okay, will be IC by IB. So you can see collector, this is your output, and base is nothing but your input. So the current gain, how much current is changed in the output side, that is the collector side, upon how much current is given, fed inside the input side, which in this case is the base current. This is your current gain factor, which is beta, as simple as that. Okay, how to remember alpha and beta in these configurations? See, beta is, the definition of alpha and beta never changes. It's always the same, whatever I gave you before over here. So do not forget this. Where did it go? Yep, over here. This definition always remains the same. It will never change. Okay, always keep collector on the top, and if it is beta, base. If it is alpha, then E. That's all. Okay, and in case of this particular configuration, when we are talking about the gain, the current gain, we usually are referring to beta. Reason? Because the output is on the collector, input is on the base. So output by input. Now check what is output, it's collector. Check what is input, it's base. What is IC by IB? That's beta. That's how it is. Okay, Sumit Bacha, is that clear? Alright, Anirudh, looks like it is fine. Great, great. Let's move to some questions and solve some questions, you will get a hang of it. An NPN transistor is there and it is biased to work as an amplifier. Which of the following statement is not correct? Okay, I think we just did this. Oh no, sorry, we did not do this, my bad. Okay, cool. An NPN transistor is biased to work as an amplifier. Which of the following statement is not correct? NPN transistor. I just gave you some statements some time back. Let me go back to those slides and show you over here. Yep, look at this. Emitter base is always forward biased and base collector is always reversed bias. Observe this. Where do the electrons flow from? Electrons always go from, in this case NPN, from emitter to base, or base to, from collector to emitter. Alright, look at this entire diagram. They go from emitter to base and they also go from this side to this side. But in these options over here, you will notice, where is it? Yep, let's go over here. Electrons go from the collector region to base. This would be the wrong option. This would be the wrong option. Observe why. I'll go back to that slide. Look at this. Okay. They go from collector to base. This is wrong. In fact, remember I had mentioned that the electrons which come from the emitter, some of them merge with the holes, some of them will get spilled over and they enter the collector. So they are going from emitter to base to collector. The electrons never go from collector to base. Look at this. That's because it is reverse bias. So it will always go from here to here. That's base to collector, not from collector to base. Hence you will see this option is wrong. This option is wrong. Rest all options are correct. Conduction of electrons leads or the movement of electrons leads to conduction of current in transistors. That's obviously correct. Electrons go from base to collector. That's also correct. Electrons go from emitter to base. That's also correct. Okay, is that fine? Cool. Trail, I'm not sure, Bindu, in what reference are you mentioning that? Consider an NPN transistor and it is used as an amplifier in the common emitter mode. The current gain of the transistor is 100. The collector current changes by 1. What will be the change in the emitter current? Beautiful question. Bindu, can you please repeat what you, in what reference did you mean it? Okay, let's try this question out. First of all, the current gain of the transistor is 100. This statement, the current gain for a transistor which is used as an amplifier. Remember I had mentioned you the current gain is beta and it is IC by IB. That's all. Now do I know anything? Yes. If the collector current changes by 1 milliampere. Okay, that means in this situation I'm not interested in the actual values but by the changes of that current. So the delta values is what I'm interested in. If the collector current changes by 1 milliampere, all right, and beta is given to be 100, I can immediately find how much is the change in the base current, and that would be 1 divided by 100, which is 0.01 milliampere. Is that what is asked? No. The question is what is the change in the emitter current? So for that, make use of this logic. The emitter current is the base current plus the collector current. So change in the emitter current is change in the base current plus change in the collector current. So change in the emitter current will be change in base, which is 0.01, this value. Change in the collector is clearly mentioned 1. So that's it. It will be 1.01 milliampere. As simple as that. Oh, not trail, trial. You can join the 1 month trial, which is there for, I don't know, maybe 1000 rupees or something. You will get all the soft copies of all the chapters. Okay, you can get it that way, Bindu. Okay. So if you join for 11th, you'll get it for 11th. If you join it for 12th, if you join the crash, obviously you'll get it for 12th and all of that. Okay, cool. Let's move on to the next one. For a transistor, the current amplification factor alpha is 0.8. The transistor is connected in common emitter configuration. The change in the collector current when the base current changes by 6 milliamperes is. Okay, let's try this out. It's again very much similar to what we have done before. The alpha value is 0.8. Now remember, alpha is IC by IE. That's what it is. Alpha is 0.8, and the change in the collector current when the base current changes by 6 milliamperes. Okay, here I don't have the base current. Okay, fair enough. Also, if alpha is IC by IE, alpha will also be delta IC by delta IE. Next thing, beta, which is delta, okay, IC by delta IB. Can I write this as maybe IC divided by base is nothing but emitter minus collector current by Kirchoff's current law, because base is the smaller one, emitter is the largest one, collector is the decent one. So emitter minus the collector always gives you the base current. What if I divide this? If I divide this with IC on numerator and denominator side, I will be left with 1 by delta IE by delta IC minus 1. Now once I get this, I can see alpha value is related over here. That's exactly the reciprocal of this. So I can very well write this as 1 upon 1 by alpha minus 1. Now take LCM, you will see that the alpha value goes on the top and it will become 1 minus alpha. That is your beta. Now alpha value is known. From this I'll find beta first, and let's see what do we do next. So beta will be alpha. Alpha is nothing but 0.8 upon 1 minus 0.8, which is 0.8 divided by 0.2, which is 8 by 2, which is 4. Beta, now you can write this as delta IC by delta IB, because beta is IC by IB, so it can also be written on as delta IC by delta IB, and this is nothing but 4. Change in the base current is 6, so delta IC by 6 is equal to 4, so therefore delta IC should be 6 4s are 24 milliamperes. So do I have that option? Yes, I have it. Yep, this is the correct answer. Yep, it is. So the point over here was that alpha was given, but base current was also given, and in base current does not come in the alpha formula. So we had to convert that alpha into the beta form, and once I get that, I know beta formula has base current. From that I can find the collector current. So that was the whole flow of this question. So it's all about using these 2-3 formulas again and again. Okay? Yes, Bindu. Yes. And best way, if you want to check out Bindu, the entire Tattva, just watch my session. You will see a glimpse of Tattva, all the problems and how it is. I have opened up Tattva and shown. Okay? Great. Yes, Sumit, this is the last session of semiconductor. Sam Kumar Jivarajpu, you can do one thing, leave a comment after the video ends. I'll definitely help you out with whatever query you are facing, because I need to explain in detail. Okay, cool. Now the last part of this chapter is digital signals and logic gates and Boolean algebra. Let's talk about it. It's a very small thing and very logical thing, obviously. Now all the electronic devices that work around you, 99% of the times what they have is something called as a digital signal. Basically they talk and communicate in zeros and ones. Now there are many advantages of using digital signals, like there is lesser noise. Also you can do many mathematical operations on digital signals easily, and there is hardly any loss of any signal even for large distances. So there are multiple ways of communicating. One is analog, other is digital. Analog is where you have a varying, a signal. It can have different values. Many values can be there, but a digital signal will have only 2 values, especially when you are communicating in the binary mode. And there are more types of digital signals where you can have tertiary and trinary and hexadecimal and so many other things. But let's keep it simple. You can have zeros and 1, either on or off. So let's say when I'm talking, I'm using so many frequencies, A, B, C, D, so many frequencies are there in my voice. But let's say I can only use one frequency, either or nothing, or nothing, like yes or no. I can't use anything else. So that's what a digital signal is all about. It's like on and off, 0 and 1, true or false, yes or no. That's what it is. So look at this. Imagine you had to communicate with someone using just true, false, yes, no, on, off, A, B, 1, 0, whatever you want to call it. It will be a crazy system or a language that you have to develop. But this is how our computers, this is how our programming languages, this is how our electronic devices understand each other. They are not humans, they are machine. This is a machine level language. Ajit, this is an English channel, bacha. Okay. So, going ahead, why do we have to study something called as a logic gate? What is this logic gate? You might have heard about this word. When you have these signals coming in, you need to operate on them. There could be some program written on some application, and this needs those signals. You want to calculate how much is the percentage of something. Maybe you have put some money in the bank. You want to calculate how much money you will get back after 5 years. You have written an application, you have written a program for that. So it needs to calculate, and it has to work on these numbers, these zeros and ones. When you want to work upon these zeros and ones, just like in your basic algebra, you have plus, minus, multiplication, division, equal to. These are your operators, right? There are these operators which are there for this machine level language, zeros and ones, trues and falses. So this machine level language needs to be performed. You need to perform these operations using a special kind of operators. Those operators are your logic gates. And there are very simple operators like AND, OR, NOT, NAND, NOR, etc., which I'll be showing you now. These operators help you to operate on these true falses, zeros and ones, whatever you want to call them, and it will give you the desired result. So when you see the motherboard or when you see these chips, there are so many operations, trillions, sometimes billions of operations being performed per second, so that you get to see whatever you are. Right now, as you are watching this video, these computer chips on my PC, on your PC or your mobile, they are performing so many operations on the audio, on the video, on the data which is sent, and that's why you are able to see that on your beautiful screen. It's crazy. So, what are the basic operations that you can perform? Okay, and I have put it up for you, a very crazy. These are the symbolic ways, just like you have multiplication, division, right, addition, etc. Same way you can perform those operations, but in a different way, and that's what I want you to see. So let's talk about the OR gate first. What is OR? OR means either this or that. I want a pizza or I want a cake. If you give me a pizza, I'm very happy. Great. If you give me a cake, I'm also happy. If you don't give me anything, I'm not happy. And if you give me both, I'm still happy because I wanted either pizza or a cake. That's it. So that's what an OR statement means. Observe. There is a power supply. There are two switches. There is a bulb. Either you turn this on or this on, the circuit gets completed and the bulb is on. If this is on or this is on, doesn't matter. If both are on, then also the circuit gets completed and the bulb is on. That's all that is there in a OR circuit or a OR gate. So let's talk about it. How do you show an OR gate? There are obviously two inputs and there will be one output over here. So these are your inputs. This is fed to an OR gate. The OR gate looks like this and you take out an output. This is, let's say, your input A, this is your input B, this is your output, let's say I call it O. So I can have something called as the truth table, which will tell me for which inputs what output I will get. For example, if my input is 0 for both the sides, for both A and B, meaning this is also false, this is also false. False or false. I asked you for a cake or a pizza. You did not give me either of them. 0, 0. Then the output is 0. I'm not happy. Similarly, if I give you a pizza, maybe I did not give you a cake. I asked you, give me a pizza or a cake. So that's it. It is still 1. I ask you, give me a, let's say, a pizza or a cake. You do not give me pizza, but then you give me a cake. That's fine. I'm still happy. You give me both. I'm still happy. Or you give me this or that. That's why the truth table, this is the truth table. It tells you how it will behave. That is called as a truth table. You have inputs, you have outputs. And there is a mathematical way of representing it. This is the truth table way. This is a symbolic way. Mathematical way of representing it is like this. You show it as A plus B is O plus. This plus stands for OR. Keep this in mind. So, interesting things that you saw over here is 0 plus 0 is 0. 1 plus 0 is OR. Read plus as OR. 1 plus 0 is 1. 0 plus 1 is also 1, and 1 plus 1 is not 2, it is 1. This is Boolean algebra. Is that clear? So this is Boolean algebra. 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 1. Do not think of it in your basic algebra terms. Sir, 1 plus 1 is 2. How is this? 1 plus 1 means 1 or 1 is 1. That's how you need to read this. I put this up for you, okay, on this slide in the printed form as well, okay, just in case you needed it. Next, AND gate. And this. Look at this. There are two switches connected to this power supply and this bulb in series. If you turn this switch on, leave that switch off, circuit is incomplete. If you turn that switch on, this switch off, still the circuit is incomplete. Only when both the switches are on will the bulb will glow. That is an AND operation. This and this should be on. I want a cake and a pizza. So the way to show it symbolically, AND gate is shown like this. So these are your two inputs. This is your output. Mathematically, you will show it A dot B. This is not your dot product. The dot stands for multiplication in Boolean algebra. A dot B is O. The truth table will look something like this. I asked you for a pizza and a cake. You did not give me anything. I'm not happy. You got me only one thing. I'm still unhappy because I asked you for both and you gave me only pizza, not the cake. Still I'm unhappy. You got both of them. I'm very happy. This is how it works. So if I put it over here in Boolean form, 0.0 is 0. 0.1 is 0. 1.0 is 0. 1.1 is 1. That's how it looks like. Crazy. Okay. So Saurav, it is usually based on Young's double slit experiment, and in the recent years there have been some questions on diffraction or in general optical part difference as well. Okay, that's your AND gate. I put it in the printed form as well for all of you. The next type of operation that you can perform is the NOT gate. Meaning, it's a very weird thing. If you say yes, you say no. If I say no, you say yes. Exactly opposite, you invert. Imagine a switch which turns on a bulb when you turn it on and turns off, or sorry, the other way around. When you turn on that switch, the bulb turns off, and when you turn off the switch, the bulb turns on. Exactly opposite. So crazy. Look at that. When the switch is off, the bulb is on. When the switch closes, then the bulb is off. It's exactly opposite. You can do it in a very simple way. Wherever it's off, you label it as on. Wherever it is on, you label it as off. So every time you think you are turning on the switch, you are turning it off. And when you are turning it off, you are turning it on. So that's how it works. So it's exactly negating it. And the way of representing it symbolically is like this, a NOT gate. This is your input, this is your output. Mathematically, you represent it with a bar. A bar is equal to O. Bar, you put a bar over that thing, that means you're negating it. So let's take some examples so that you understand it. So if you want to draw the truth table of the NOT gate, it's going to be very simple. If you give 0 or if you make it false, the output is true, or basically 1. If you give 1, the output is 0. That's how it works. So if you want to write it over here, 0 bar is 1, 1 bar is 0. As simple as that. Is that okay? So that's your NOT gate. So the three different gates that we have seen till now: OR gate, all right, you have seen OR, this or this, then AND gate, this and this, and the last one is the NOT gate. Now there are more complex gates as well, like XOR, XNOR, NAND, NOR, so many other gates that you can form. Like for example, this one, NAND gate. NAND is nothing but an AND gate with a NOT in front of it. Meaning you have your regular AND, you put a dot, it becomes a NAND. Meaning wherever the output was expected to be 0, you'll make it 1, and wherever the output was expected to be 1, you make it 0. How did the truth table of an AND gate look like? For 0, 0 it was 0, 0, 1, 0, 1, 0, 0, 1 and 1, 1. Exactly negated. So that's your NAND gate. So NAND is nothing but AND plus a NOT gate. As simple as that. Yes, Pooja Dura, you can definitely. Similarly, a NOR gate is a OR gate with negated input. That's it. You have a OR, you put a dot, whatever output you get for OR, you just negate it, you invert it. Wherever you would expect 1, put 0. Wherever you would expect 0, you put 1. As simple as that. So you put a bar over there. Let's solve some questions so that you will get a hang of this. Now, before going there, I have an important formula that I want to show so that you remember this and it will help you solve so many questions. So one of the most important formula is, it's called as the De Morgan's law, De Morgan's formula. So A plus B bar is A bar dot B bar. So the bar is there on the entire thing. When you take it like this, when you split it up, you can put a dot and you can put the bars on both the sides. Very interesting formula. It works the other way around also. So if you have A dot B whole bar, it can be written down as A bar plus B bar. Very, very important formula. Okay, so this is also called as your De Morgan's law. Very, very important. Then there are some more formulas which are very easy to remember, or you can even derive it on the spot or even think about it logically. Like for example, A dot A. What do you think A dot A will be? Think about it. Tushar, just follow my 45 days strategy which I had given few days back. I given the detailed timetable and the methods to complete the entire syllabus in 45 days. Just watch that video. It's there on this channel. So what will be A dot A, my warriors? A dot A means A and A. 1 and 1. What is 1 and 1? 1. 0 and 0? 0. So if A is 0, 0 dot 0 will be 0, which is A. If A is 1, 1 dot 1 will be 1, which is again A. So A dot A is basically A. Is that clear, my warriors? Cool. Similarly, A bar bar, meaning negation of A. It's like negative of negative. That will be positive. So not of 0 is 1, not of 1 is again 0. So you will get back that number A. Is that understood? Very good. Excellent. A. Next, let's see if you can get this. A plus A. What will be A plus A? Come on, my warriors. You will be like, sir, it is 2A. Well, hold on. A plus A. Think about it. 0 plus 0. 0. 0 or 0 is 0. 1 plus 1. 1 or 1 is also 1. So A plus A is A, not 2A. Okay? So it's crazy, but it works. So if you remember these few things, trust me, most of your jobs will be done. Is that clear, my warriors? Okay? So I can give you some examples over here. Just think about it. For this one, 1.1, 1. 0 dot 0 is 0. So if A is 1, the output is also 1, which is A. If A is 0, the output is 0, which is also A. For this one, look at this. 0 plus 0 is 0. 0 or 0, or read it as or, is 0. 1 plus 1 is 1. Right? Do not forget, 1 plus 1 is 1. 1 or 1 is 1. So it is still A. So it works for both the cases, and there are only two numbers which are possible, either 0 or 1. Hence it works. If you remember these few things, trust me, most of your jobs are done. Is that okay? Clear? Excellento? Let's solve some questions. You will get a hang of it. The given figure shows the waveforms of two inputs A and B that form the output Y of a logic circuit. The logic circuit is, look at the input, 0, 0, 1, 1, 0, 1. This is high, okay, 1. Consider the signals as 0 volts, high volts, 0, low volt, false, high, plus, okay, true, 1. All these are same things. Keep this in mind. So observe these two inputs and figure out which kind of a gate does it represent. So the best way to do that, start writing these numbers. This is 0, this is 0, this is 1, this is 1. This is 0, this is 1, this is 0, this is 1. The output, what is the output looking like? 0, 0, 0, 1. If you draw the truth table, it becomes very obvious that the truth table is 0, 0, 0, 1. And the input side truth table, 0 and 0 is 1, 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. Which kind of a truth table it is? Which kind of a truth table it is? Obviously, it is a truth table for a AND gate. Correct? It's an AND gate. I hope this is clear. 0 and 0, 0. 0 and 1, 0. 1 and 0, 0. 1 and 1, 1. Hence, it's an AND gate. This is how the signals are going to look like. Perfect. Moving on to the next one. Here is a logic gate. The output in the circuit can be represented in the mathematical form. In which way? Which of the following formulas represent this circuit in the mathematical way? This is a logic diagram. This is the mathematical expression. Which is the correct representation of this? Okay, the best way to look at it, start doing it part by part. Observe, B not, B is negated. So this part over here is nothing but B bar, you are negating it. Here, this part, think about it. What is this? This is AND gate. AND means dot, correct? You are dotting it with C. So B dot C. Great. That is fed as an input to this gate. This is an OR gate with a NOT in front of it. Interesting. I'll keep that aside. So think, if this is an OR gate, this is an OR gate, the one of the input is this one. That means this plus OR with A. A is the other input. That is what this is. Lastly, do not forget there is a NOT over there. There is a NOT over here. So if this is also present, this is NOT. That means the entire output has to be inverted. So put a NOT over there. So do you see which option is correct? D option, A plus B bar dot C. A plus B bar dot C. That's option D, right? Is that clear? That's how you go step by step. This is an easy way of representing. This is a logical operation, symbolic way of representing the same thing. So that's how you convert from this to this or this to this. You can have both kinds of question. This is given, you have to write this, or one of them is given and there are 4 logical diagrams and you have to figure out which one is correct. Either way, you will get it. Fair enough? Let's move to the next one. In the circuit shown, the 2 input waveforms are applied simultaneously. The resultant waveform is, observe this logical diagram, which is the correct output that you will get for this particular thing. Okay, here is what we will do. We'll make a truth table. Making a truth table always helps. I have A and B. Okay, and let's make a truth table like this. A is 1, B is 1. A is 1, B is 1. A is 0, B is 0. Okay. A is 1, B is also 0. A is 1, B is 0. A is 1, B is 0. Lastly, A is 0, B is 1. These are the inputs. That's what I get from this diagram. Good. Next, there is a NOT gate in front of A and in front of B. This is, if this is A, this is A bar. If this is B, this is B bar. Those are the inputs for this gate. So let's try to find out what will be A bar and what will be B bar. A bar is negation of this. So 1's negation 0, 1's negation 0, 0, 0, 1, 1. This will be 0, 1. This will be 1, 0. Those are the inputs. Last thing, those are the inputs for which gate? This is a OR gate. So you have to perform OR operation on these two, not on these yellow numbers, the green ones. 0 or 0. This, remember, is a OR gate. 0 or 0, 0. 1 or 1, 1. 0 or 1, 1. 1 or 0, 1. So what does it tell you? It's low and then it becomes high and it stays like that. It's low and then it becomes high. So do I have an option like this? Yes. This is the one. Correct? You might be like, sir, it falls down. Yeah, that falls down after this line. So after this line, it will fall down, obviously. So that is the correct answer. You got it? Clear? Yes, Vishwas, it is. It is option A. Perfect. Let's move on to another question coming up on your screen. In the Boolean algebra, this entire expression equals to which of the following options? A bar dot B bars bar dot A. Crazy. Let's try to do this question. First of all, using De Morgan's principle, which I have taught you, A bar dot B bar is nothing but A plus B whole bar. Remember, I just told you about it. If the bars are separate, you can bring them together, or if it is together, you can separate them out. Using this over here, can I not say this entire expression actually is nothing but bar of A bar dot B bar is nothing but A plus B bar, the whole thing dot A. This is what it is. Bar of a bar, the bar goes off. So hence, this will be just A plus B dot A. Correct? Everybody fine till here? Cool. Next, multiply this. A plus B dot A. So I can write this as A dot A, just this is a bracket, I'm opening it up, plus B dot A. A dot A, what is A dot A? I just told this to you. In case you have forgotten, let me bring it back, refresh your memories. A dot A is just A. So hence, over here, A dot A, I'll just put it as A, plus B dot A, I don't know what to do with it, I'll just put it as B dot A. Now again, I'll take it as common. A is common, 1 plus B. What is 1 plus B? This is an interesting thing. What will be 1 plus B? Guess what? 1 or B. Okay, if you do not know what 1 plus B is, I'll help you out a little bit. Observe this. 1 plus B, right? It is 1 or B. Now B can be either 0 or 1, right? So 1 or 0 is 1. B can be also 1. So 1 or 1 is also 1. In either case it is 1. So 1 or B is always 1. Keep this in mind. 1 or B, 1, true or anything, does not matter. It will be always true. So hence 1 plus B is nothing but just 1 itself. So there was a dot here. It's 1 itself. It's crazy. 1 plus B just becomes 1. And A dot 1, 1 dot A is just A. Hence, the correct answer will be option B. Done, done, done. It's a crazy operation and it's all logical. Okay, cool. So that was the answer like you saw. And please join the Telegram channel so that you get the entire session PDF, my handwritten notes for today's session, also important updates and announcements, including the solutions for today's homework problems, which have been put up right over here. Post the answers in the comment section below. This is your second homework question, and this is your third homework question, and this is your fourth homework question, and this is your, this is not your homework. But yes, this is something which you need to join if you want to cover the entire syllabus before JEE begins. And JEE is not far away, like we all know. Most likely first attempt is in April, first week. So we have a crash course which has just started today in English, and you will get 20 tests, you will get assignments, you will get live plus recorded classes, all for just 8,000 rupees when you use my coupon code SHHPRO. So it's all there in the description box. If you are watching this lecture right now, right over here, all you need to do is, go to the description box, and that's over here. And what you need to do is click on this link. There is also a CBSE Term 2 crash course which is available. You will see all the benefits, like say for example, there is a NEET crash course as well available. You will get the same discount using my coupon code. Okay, so let's say you choose JEE crash course. You can see it starts on 21st Feb, that's today. If you're watching this lecture later on, you can still join this. 75 live classes. Obviously the teachers who have been training kids for a long time are only there, who are experienced in crash courses, and that too this batch is in English medium. 20 test series, you decide when to attend it. And also you get the report cards, all the analysis, everything that you want. It says 9,000, but when you use this coupon code and when you say buy now, you enter your details, it comes down to 8,000 or even lesser than that, depending on when you are watching this video and which offer is being rolled out. Okay, so go ahead. There is also doubt solving which is available in this crash course in the class as well as outside the class. Okay, so you have any doubts, you can ask it any number of times, and you can just get it resolved so that you don't have to disturb the flow of the class as well. So that's it from my side. And yep, so any doubts that you have, like Boomer and Shyam Kumar, let me know in the comment section. I'll definitely respond to it, and you can also reach me out on my Instagram handle as well. So thank you. This was the end of Pathfinder series. Now we'll be doing more of revision via problem solving, sprints, mock tests, one shots, and so many other things. So thank you for tuning in. Take care. Bye bye. Hasta la vista. This was Shreyas here.